In this video, we're going to take a look at another number that's associated with a discrete random variable, and this number actually requires us to use the mean, which we previously defined. Now, there are a few more steps in computing this number that we're going to call the standard deviation. So I'll define the things as needed, and then once we've defined the entire process, we'll have an example completed, and then I'll give you a brief interpretation of what this number represents. Right? So let's start by setting the scenario up. So let x be a discrete random variable with possible values. So with possible values. And then again, remember we use our little x to represent those. And I'm just going to say like x1, x2, and so forth. And again, that list, it could be finite, which means the discrete random variable is a finite random variable, or it could be countably infinite, which means the list would go on forever. But either way, we have the possible values here, and corresponding probabilities, right? So corresponding probabilities. Now we have different ways that these probabilities can be denoted, right? There's lots of notation here in probability. So we could use this notation, which we've used the little f to represent the PDF, but just for simplicity, I'm just going to kind of abbreviate that with a single p with a subscript, right? It's just a little bit easier to write the formulas down if I'm using these as my possible x's and then these as the corresponding probabilities, right? So the first thing we need to define before we get to the standard deviation is something called the variance, right? So the variance of x, and there's several notations for the variance. You can pick whichever one you like. So the first one is just v of x. That's obvious, they're using just the first letter. The other way, sometimes you'll actually just see VAR, again, just an abbreviation of the word variance. But then the third one is a little strange. Like, where do we end up with a Greek letter out of this? Well, Greek letter sigma, but then it's squared, and then you might possibly put the x as a subscript, again, if you need to specify that this is the variance of this particular random variable, right? So these are all the different notations. I don't really have a preference one or the other. We'll probably use this one the most, however, right? So the variance of x denoted in one of these three ways is defined as, so let's write it down. So I'll use this notation. So your sigma squared of x. And again, we'll probably, as we go through the example, we'll probably drop the subscript here, because we're not going to be working with several random variables. It's only when you want to be precise to say here is the quantity for this random variable, that's when you would indicate it using a subscript. But here's how the variance is defined. It is also a summation, and it's still a summation over all possible xi's. Well, what do we sum? Well, we're going to take each possible value of x, and we have to subtract the mean, right? We have to subtract the mean, right? And then we square those differences, and then not lastly, and then next we multiply each squared difference by the associated probability of that particular x value, and then sum all these products up, right? So that is our standard, our variance. This is how the variance is defined, right? Well, to illustrate this, since we used we used a specific probability distribution function to illustrate the mean, let's use the same one to illustrate the variance and then subsequently the standard deviation. So let's look at an example of this. So I'll remind you of that one, that distribution. You might have it in your notes, right? And this random variable, it had only 4 possible values. So here are the x's and here are the p's. Right? So it was 1, 2, 3, 4, and then the probability that x is equal to 1, that was let's see, that was 0.1. The probability that x is equal to 2, that was 0.3. The probability that x is equal to 3, that is 0.2. And then the probability that x is equal to 4, that's 0.4. Right? And just as a quick check, it's always important to, just double check that you're satisfying. We can go all the way back to the axioms of probability, or now we have these properties of both the PDF and the CDF. So if we stop at the properties of the PDF, all these probabilities are between 0 and 1, so check, and they all add up to 1, check. So we have a valid PDF right here for this discrete random variable, right? Now, we have the mean from a previous set of calculations, but just for more practice, even though it's the same one, let's just remind you of how you compute the mean. And in the calculation here, since I'll be writing the mean several times, I'm not gonna emphasize the sub x anymore, because there's only one random variable that we're looking at, and therefore only one mean, right? Or expected value. But hey, remember, this is the definition of the mean. It's another sum, and now this one will go from 1 to 4 because I know specifically how many possible values there are. So this is where I will use the limits on my summation, and the calculation is fairly straightforward. You take your xi and you multiply it by each probability and then take the sum. If you remember, I'd used the analogy between this type of calculation and computing a dot product. It does look like a dot product, doesn't it? You take pairs of numbers, you multiply them together, and then you take a sum. It's exactly what we're doing here. So it's 1 times 0.1 plus 2 times 0.3 plus 3 times 0.2, and then finally 4 times 0.4. And if we double check this, and with what we got before, and if we check our calculations again, you'll see that this is 2.9, right? So the first part here, is if you don't have the mean, you have to find the mean before you can do all this other stuff, right? So now let's do all this other stuff. Now, a nice way to keep track of your work when you're computing something like a variance and then subsequently a standard deviation is that you can set things up in the form of a table. But what I'm going to do is I'm going to have the values, now instead of as rows like this, I'm going to set them up as columns. So I'm going to have a column for the x's, or specifically the xi's. In this case, 1, 2, 3, 4. And then each column will actually represent the next step in the process. So I'm not going to put a column for the probabilities just yet. In fact, I don't really need to state that column again. But the next thing I have to do when you look back at the formula, it says you have to take the difference between each x, each possible x, and the mean that we just computed. So to fill out this first column, I have to take each x value here, 1 through 4, and subtract the 2.9. So if I take 1 minus 2.9, I'm going to get negative 1.9. If I take 2 minus 2.9, I will get negative 0.9. If I take 3 minus 2.9, I get a pretty small number. 0.01, or I'm sorry, 0.1, and then if I take 4 minus 2.9, I will get 1.1. So this column here, literally when we take each x and subtract the mean, it's sometimes referred to as these are the deviations. So these are deviations from the mean. And essentially, it is a signed difference, SIGNED, basically saying that some are positive, some are negative. And the fact that this is negative, it means that this possible value of x is less than our theoretical mean. And this one being positive means that this possible value of x is greater than this theoretical mean, right? And again, it's essentially we're just saying like how far away from the mean is each possible value of x and in what direction. So the negative ones would be to the on the number line, the negative ones would be to the left of the mean, and then the positive deviations would mean that those x's are to the right of the mean. Right? But the next step is to square this, right? So it's xi minus the mean, and we have to square each of those deviations. And unsurprisingly, they're called squared deviations from the mean. So squared deviations from mu, or mean. And so let's go ahead and square them. So let's do the calculation, and then I'll give you a little bit. I can't give you too much of a rationale here, but I'll try my best, right? So if we square the negative 1.9, we will get a positive 3.61. If we square the negative 0.9, we'll get a positive 0.81. If we square the 0.1, we'll get 0.01. And if we square the 1.1, we'll get 1.21. Now, again, and I'll say more when we interpret what this eventually what the standard deviation is. But basically, so we have this sort of theoretical average, right, which we call the mean or the expected value. And this calculation right here, again, over here, this gives you the deviation. But many times we don't really care if the x value is either less than or greater than the mean. We just want to know how far the x value is from the mean. So we want to somehow get rid of the negative values. Well, in terms of very simple operations that can be used to get rid of the negative values, we could square, right? Another simple thing that we could do is to take the absolute value, right? We could just take the absolute value and just look at the magnitude of these differences, these deviations, instead of a squaring. But here's one little explanation as to why the square is preferred in many instances over the absolute value. And it goes back to a basic calculus concept. Your power function, your x squared, your squared power function is always differentiable. So if you're looking for some type of, let's say, function that and down the line when we start doing more sophisticated things, or maybe even beyond this particular course where we start to do more sophisticated things, if differentiability is an important property in that work, then we would go for the square function as opposed to the absolute value function, because you remember absolute value functions have those sharp corners. So if differentiability is a property that we would need to use later on, then we would want to define this in terms of the square as opposed to in terms of the absolute value, right? So there are a lot of little things here. It's like, okay, why do we do this? Okay, well, why don't we do a fourth power, if that's the case, or some other even power. Again, there are lots of little reasons why we would want to settle on this particular type of squared deviation. It has a lot of mathematical properties that are helpful in future work. And to be frank with you, you're not going to see that work in a course like this that's a little bit more advanced. But again, I always like to try to give you some explanation as to why, right? Maybe it doesn't completely answer all your questions, but at least a partial answer is better than none at all. All right, so those are the squared deviations. The next step now is I have to take each squared deviation, so each xi minus mu squared, then I have to multiply it by the corresponding probability. So in terms of, now this is what I will write out. So we're going to take the 3.61 and multiply it by the 0.1. So we're looking at the probability that corresponds to an x value of 1 and multiplying that probability and that squared deviation. So it's this, and then that ends up being 0.361, right? And then just repeat the process. So again, take the squared deviation from 2, or of 2 from the mean. That's the precise way to say it. So 0.81 times, and then that corresponding probability, that's where we use the 0.3. So 0.3. And then that gives us 0.243. And then if we take the 0.01, and you notice how small this squared deviation is? And that's because the 3 is very close to the 2.9. It's relatively much closer than the 1. And that's why this squared deviation is relatively much larger than this one, right? So take that 0.01 and multiply it by 0.2, and then that gives us 0.002. And then finally, take the squared deviation of 4 from the mean, which is the 1.21, and then multiply it by the our last probability there, the 0.4, right? And then that gives us 0.484, right? So now, if I take this final column and I sum it up, that will give me the variance. So sigma squared, again, let me write the formula. It's your each x minus the mean squared times the associated probability, and here in this case the sum goes from I goes from 1 to 4, and when we add those all up, what we end up getting is 1.090. All right, so that is our variance, and it's a little bit harder. I mean, we can, and we could come up with an interpretation, but really what we want is the standard deviation. So now that we know the variance, let me show you what you do with the variance to find the standard deviation. And it's as simple as a simple root. So the standard deviation, of x, and there are several ways that it's denoted. Now there are two words here, standard deviation, so you might actually see SD of x, but more often than not what you see is just the sigma written by itself without the square. So it's either denoted this way or just sigma like that, and this then tells you what you need to do to get the standard deviation. If you have sigma squared, which is the variance, and you want to find sigma, think about the operation that you would do to get rid of the power of 2. You would take a square root, and that's exactly how the standard deviation is defined. It's defined as the square root of the variance, right? So your standard deviation is defined as, let's see, so sigma, which is the square root of sigma squared, right? And you might say, well, okay, the square root could this thing ever be negative? Like, could the standard deviation be undefined? Like, what if you get a negative under the square root? Well, that can't happen. And that was another reason why we ended up, even though we had these negative deviations, we ended up squaring them. So this column is always going to be filled with positive values. And then the fourth column here, we multiply pairs of positive values. We know our PDF values are always positive. They're always between 0 and 1, right? So these products are always going to be positive, and you're taking the sum of positive numbers. So your sigma squared in general is always going to be greater than or equal to 0. Hence, the standard deviation will always exist, right? For these types of calculations, right? So for this, we can then say, so for this example, our standard deviation is the square root of 1.090. And unless it works out almost, I'll say miraculously, that you have a perfect square under the square root, you're always going to end up with some irrational number as your standard deviation. So in this case, I'll go at, since all the other numbers were accurate to the 3 decimal places, in fact they were precise to 3 decimal places, I'll go ahead and round the standard deviation to that level of accuracy, and it's 1.044, right? So what does this number mean? Okay, so what I'm going to do is draw our number line, right? So here's our number line. And I'm going to go, so I'm going to identify the possible values of x. So 1, 2, 3, and 4. Let me take off the little piece there that I don't need. All right, so these are our possible values of x. So every time we do the experiment, we're going to get one of these 4 values. Right? One of those 4 values. Previously, we talked about what the mean could mean. The 2.9, which is, roughly around here, is this location, the 2.9, which is our mu, right? Our mean. It represents the point of balance where if I had a horizontal axis, and if I were to put 4 masses, and the masses are equivalent to the probability. So the point, was it 0.1, a mass of 0.1 here, and then the 0.3 here, and the 0.2 here, and then the 0.4 here, then this location would be the point at which this system, this physical system, would be in equilibrium, right? But the thing is, so when we compute the standard deviation, so now, so the mean is fixed, right? When we compute those deviations, what we're computing essentially is the distance from the mean, or from each point to the mean, right? So, that's one of the deviations. This is another deviation, right? And these are, because these x values are bigger than the mean, then the deviations are positive. They're going this way. To the other values now, this is the deviation, and then we can see the really big one here, right? So the standard deviation is a measure of, on average, how far is each possible x from the mean. So let's say you think of the mean as some measure of the center, like where are the values roughly centered, right? They're roughly centered at 2.9. Well, the standard deviation gives you, on average, what is the deviation from that center, right? So the standard deviation, so the standard deviation gives the average deviation of the possible values, right, from the mean. So it kind of like averages up all the deviations there. So all those distances in green, they're measured, and we kind of average them. We weight them based on those probabilities, and we come up with this number, right? So from the mean. And what it means is, and then I'll sketch a couple more things that don't necessarily reflect the example, but will illustrate, again, other ways that you can interpret it. So the smaller the standard deviation, the closer all the possible values are to the mean. So it's like there's very little variability in each of the values. So they're like clustered together. So let's say I'm going to draw two number lines here, and we're going to have, some possible x values like here, and then again I'll use that as your mean, right? And then again, let me indicate the deviations. I'll just indicate a few of them. So maybe that one, and then maybe that one, and so forth. Actually, I guess I could just go ahead and do them all. So here are those deviations, right, from the mean. Right? Now, one of the really useful things of the standard deviation is when you want to compare the amount of variability, like the amount of randomness in different random variables. So like, is one more random than the next? That might be an important question. So if I have something like this where these are my possible values, right? So they're still discrete, and let's say that the mean ends up being like right in the middle, like right here. Now look at these deviations compared to these deviations. These are going to be much smaller, right? These distances are going to be much smaller. So because the distances are smaller, when I square them, I'll still get smaller numbers. And then when I add them up, that sum is going to be smaller. So the variance in these is going to be bigger than the variance in these. And hence the standard deviation is going to be larger in a distribution that looks like this versus a distribution that looks like this, right? So if this, for instance, has a standard deviation, let's call it sigma 1, and this has a standard deviation of sigma 2, what we can say is sigma 2 is definitely going to be less than sigma 1. So this random variable exhibits more variability than this one, right? So if I call this x1, call this x2, let's write down both of those things, right? So since the possible values of x2 are more tightly clustered around the mean. So both of the means, I'm using, again, the same blue vertical line, so are more clustered about the mean. right? Then the standard deviation for the second set of, or the second random variable here is going to be less than the standard deviation of the first one, right? So whatever the number comes out to be, I know this comparison will always be true. So moreover, this means that x1, that random variable exhibits more variability than x2 does. It's like it covers a larger range of possible values. Even though they're discrete, right? You can see that it covers a wider range than these, right? So moreover, um, the distribution, like I'll just say the distribution of x1 exhibits more variability than that of x2. And by more variability, it just means that the possible values, they cover a wider range, right? So there can be these large swings going from this x value on one trial versus this one on another trial, where over here you don't have that great variability in terms of the range that the numbers cover, right? And that's what the standard deviation, it is a measure of the variability. And you can use two or more of these numbers to say, hey, this distribution it tends to be more variable than this one, right? So it's an easy comparison, but it takes a while to kind of get there. So we have to talk about like what these deviations would normally mean. And then why are they useful? Well, they're useful in the sense that they can measure variability. So probability gives you a measure of the variability of just one random variable. But then if you want to compare several random variables to say, hey, this one seems to be more variable than the other one, then we would use a measure like the standard deviation. And there are other measures you can use as well, but the standard deviation is one of the standard ones, right? So hopefully that's helpful, and I'll see you in the next video.